Today's video is about acid-base reactions. In the second part of Chapter 4, we're going to talk about three important classes of chemical reactions. So one of the most important of those classes of reactions involve the reactions between things that we call acids and things that we call bases. So what are these guys? Well, acids and bases are categories that we humans have invented, right? So they're constructs. But they're categories based on properties of materials. So if things have this certain list of properties, then we're going to call it an acid. If things have a certain other list of properties, we call them a base. So for example, acids tend to taste sour and bases tend to taste bitter, though I don't recommend that you try tasting chemicals on your own. Acids have other properties, like they tend to corrode metals. So these are examples of some of the properties of acids and bases, and we'll learn more about them as we go through the year. But what we're going to look at now, in addition to these categories, we want to come up with a good definition for what makes an acid an acid. So in addition to their properties, that's how we put them into these different categories, we want to know, well, what is it that makes an acid, and a base, a base? And there's some different theories about this, and so the first one is attributed to this guy named Arrhenius. So Arrhenius, that's supposed to be an R there, isn't it? Okay, Arrhenius, and there's an I, says this. Arrhenius says that an acid is anything that makes H plus ions when dissolved into water. So if you dissolve it into water and it gives you H plus ions when you dissolve it, it's an acid according to Arrhenius. And Arrhenius similarly has a definition for a base. Arrhenius said a base is anything that makes hydroxide ions in water. So you'll typically hear us talk about these two chemical species when we're talking about when we're talking about acids and bases. So this is the Arrhenius definition, really, not quite a theory, the Arrhenius definition of what acids and bases are. So acids are anything that give you this, bases are anything that give you this. So by looking at chemical formulas, sometimes we can tell what those are. So here's an example of the thing that we've learned to memorize already as an acid, so HCl. Now in water, protons don't exist really by themselves, right? So what is an H plus? Well, an H plus is a hydrogen atom which is made up of one proton and one electron. But because it's H plus, you take that electron away, so this is just a proton. And a proton is a pretty small thing, and if you put that in water, it's going to associate itself with some electrons. And we can sort of see how that goes by writing a reaction that looks like this. So what's going to happen is this HCl is going to dissociate into water, and it's going to come apart. So H plus plus Cl minus, and that's how we get these H plus ions and water. Now I just told you that the H plus probably doesn't really exist by itself in water, but we will sometimes frequently write it that way. But another way that we might write it is to imagine that this H plus connects itself with one or more water molecules, and we're going to just write it connected with one water molecule in this example. So we end up with H, and you're going to add that to an H2O, and so we get H3, still have the one O, now we've added a plus charge to that. So this is another way of writing that same species. And this chemical species right here, this H3O plus, is known as hydronium. So if you hear a chemist talk about hydronium ions or hydrogen ions or protons, they're really talking about the same thing, the thing that is the acidic species in water. So we've made this hydronium. Now the Arrhenius definition is not the only definition of acids and bases. So we're going to scroll down here and look at another definition of acids and bases. This definition is due to these two chemists, Bronsted and Lowry. So that's supposed to be dashed there. Anyway, Bronsted is one Danish chemist, and Lowry is an English chemist, and working independently, they came up with this definition. And they say that an acid is a proton donor, an H plus donor. So if it gives an H plus away to another chemical in a reaction, we're going to call it an acid. And a base then is the opposite of that, and a base is an H plus acceptor. So that just means that it's going to take an H plus. So another way of thinking about these things is acids are H plus givers, bases are H plus H plus takers. All right, so we can see again how that works using that reaction that we just looked at, HCl plus H2O. Right? Now in this case we're going to imagine that this guy is the acid. That's an acid. So it's going to be an H plus donor. And what it's going to do in this reaction is it's going to donate a proton, an H plus, to water. When it does, it's going to make hydronium, right? That's our acidic species, another word for our acidic species in water. So we make hydronium, and we also make chloride, Cl minus. So if this is the H plus donor, then it turns out that water is really acting as the H plus acceptor. So water in this chemical reaction is acting as a base. Now we don't normally think of water as having properties of a base, but in this reaction it is functioning as the base according to this Bronsted-Lowry definition of what makes an acid and a base a base. So we're going to look at some other important types of chemical reactions, and that's what happens when you take an acid and a base and put them together. So this is one kind of acid-base reaction. We're going to look at a particular one called a neutralization reaction. So a neutralization reaction. So in a neutralization reaction, what we're going to form, we're going to react an acid and a base together, and in the course of this reaction, we're going to come up with something that has properties of neither an acid or a base, something that is neutral. We say something is neutral if it is neither an acid nor a base. So a neutral solution will have properties of neither an acid nor a base, be something different altogether. And so what we tend to produce as a product of this reaction is a salt. So you may think of salt as table salt, but salt to a chemist really means a category of compounds. And these categories of compounds are ionic things, ionic compounds, that you form when you react an acid plus a base. And the other product of this reaction is water. So this is a very typical pattern that we see in acid-base reactions. It's called a neutralization reaction. So let's look at one in particular. So here's the formula of an acid, HCl, and here's the formula of a base, NaOH. All right, because if we were to put HCl in water, now HCl is normally a gas, but if you dissolve that gas, that molecule, that molecular compound, into water, it's going to dissociate into ions. It's going to give you an H plus ion and a chloride. So that makes it an acid according to the Arrhenius definition. And sodium hydroxide, according to the Arrhenius definition, when you dissolve it in water, it's going to break apart into sodium cations and hydroxide anions because it is a strong electrolyte. Alright, so when these guys react, we're going to imagine that what happens is the H plus ion from hydrochloric acid is going to replace the positive charged sodium that's in sodium hydroxide and vice versa. So the sodium is going to replace the place of the H in HCl. So we end up with NaCl when we switch these guys, and HOH, right? H plus OH, and H plus OH is really just another way of saying water, H2O. So there we go. Now this kind of reaction pattern is an important reaction pattern. Give us a little more space here. And it's one that we will come to call double displacement. So this is a double displacement reaction. You'll sometimes hear this called a double replacement reaction. That means the same thing. So all we're going to do is exchange the positions of the cationic species in the chemical reactions. And so this is the product that we end up with. So NaCl is table salt. It's one class of a compounds called salts. So let's look at another reaction. So here's another kind of reaction. Let's look at the reaction between sulfuric acid, H2SO4, and another base. We'll use KOH. What we'd like to do is predict the products of this reaction. Alright, so we're going to exchange the places of the cationic species. So if we think about H2SO4, right, this acid, we learn to name this by thinking about, oh, it's some acid species, H plus, that's paired with this polyatomic ion, SO4 2 minus, sulfate, right? And we need two of these H pluses in order to do that. So in this neutralization reaction, we can react two of these hydroxides with two of these H pluses. So we're going to make a salt. We're going to replace the K with the SO4. So what's the formula of the ionic compound you get when you have K with a positive 1 charge and sulfate with an SO4 2 minus charge? Well, you cross your charges and you have to have two potassiums to offset the negative charge on sulfate. So we end up with K2SO4, that is our salt, and then we make water, H2O, right? And then we need to balance this a little bit. So we're going to need 2 KOHs, and then we're going to need 2 of these hydroxides to react with the 2 H pluses that are in this sulfuric acid. So now we've balanced the reaction. That all looks good. 2 sulfates. One sulfate, 2 hydrogens, 2 hydrogens, 2 hydroxides. Yeah, all right. So that all looks good. Oh, wait. No, we got 2 water molecules that we're going to make, so it's not good. There we go. All right, so now it's fabulous. So this is a double displacement reaction. Acid plus base yields salt plus water.